We're going to cover valve design in Matlab. In case you missed the prior lecture, there is a tutorial on the equations that we use for the valve design, and so I recommend going back and viewing this tutorial lecture if you haven't seen it yet. Okay, so let's go on to just review some of the equations from that lecture. We have our valve design equation, and that is the Q, or the flow rate through the valve, is equal to a CV, a constant, times a lift function. Okay, and that's a function of this lift here, times the square root of delta P across the valve divided by the specific gravity. And so this is a valve design equation it's commonly used. And what we're going to do is try to understand what is the installed versus non-installed characteristic of the valve. And the end objective here is that when we install the valve, we want it to have a fairly linear profile. Okay, so this would be a linear profile in lift. Okay, so lift versus flow. And the reason why we want to do that is because then we can design, for example, for a flow controller, the gain is not going to change very much depending on which region we're in. Okay, so it's going to be easier to tune the PID controllers and have one value that's going to work across a wide range of lift versus flow regions. Okay, so what we're going to do is just come up with an example problem here just to show this, and then simulate it in Matlab. So this is our valve. Okay, and let's say we have a pump, and this pump delivers 200 bar, for example. And I'm just going to put this into a flow loop, and let's say we have let's say a heat exchanger, for example. Okay, so we have some process fluid coming in, and then we come out and then go to a cooling tower, for example, and then back to our pump. Okay, so this would be called our system. And let's say that the flow rate through the system is going to be equal to a constant, I'll just say C1, times the square root of the pressure drop across the system. Okay, so we're going to be putting in a valve here to be able to control the flow. So let me just put in a valve. Erase this. Okay, so we have a valve, and so we have some of our pressure drop is going to be across this valve, and then the other pressure drop is going to be across our system, okay, or equipment. Okay, so we have a total pump pressure. Okay, so delta P total is going to be delta P of valve plus the delta P of our equipment, and we know that this is going to, let's say it's just going to remain constant at 200 bar. Okay, so we can control the flow rate by adjusting the position of the valve. And okay, so let's go ahead and just solve for both of these cases, for delta P of the valve and then also delta P of our system. Okay, so I'll make this just a little bit smaller here. Okay, so I'm going to take this equation and just rearrange it to solve for delta P of the valve. And so that's going to be Q divided by CV, and then I have my lift function. I haven't said what that lift function is going to be, but then that is going to equal the square root of delta P across the valve times the specific gravity. If I just go ahead and square both sides, okay, and I'm just going to square that. Okay, and then multiply by my specific gravity, and then that is going to equal delta P across the valve. Okay, so as the flow rate changes, I get an expression for the delta P across the valve. And let's do the same thing for the equipment as well. Okay, so then in that case I have delta P across my equipment is going to equal Q divided by C1, and I'm just going to square that to get rid of the square root. Okay, so I have a delta P across my equipment and a delta P across my valve, and then I'm just going to go ahead and substitute these in right here to my total pressure equation. Okay, so I know that 200 equals, and then I'm going to have GS, specific gravity, divided by CV FL, and that's going to be squared. And I'm just going to factor out the Q squared here. Okay, so I have an expression for lift versus Q, and then if I just divide that, I have, and just rearrange it slightly, I have 200 divided by this expression. Okay, so I have my expression here for Q as a function of lift. Now this is for the combined system, is valve plus equipment. Okay, so let's just implement this in Matlab, and we're going to implement this equation and also look at the valve by itself. Okay, so let's just go ahead and look at the valve by itself as if we had a non-installed system. So what we're going to do is, first of all, pretend like we don't have any equipment there at all, and just look at the flow rate through the valve as I change the lift, and then we're going to add the equipment back in there. Okay, and look at the whole system. Okay, so let's go over to Matlab now, and we will first of all just open up Matlab, and then we're going to create a new script. Okay, and we're going to be using some functions as well here. So I'm going to just change my directory. I'm going to go, let's just go over to my desktop. Okay, let me select that. Okay, so I'm in my desktop, and then I'm going to create a new script. And I'm just going to go ahead and save this right now. I'll call this valve design. Okay, so I have a new script called valve design, and one of the things I like to do first of all in any script is just go ahead and close everything, clear everything. So I clear all the variables, I close all the plots, and I also clear my workspace screen. Okay, so that's what CLC does, is clear the workspace screen. And I can also put comments. So I'm going to put lift functions for two different trim types. Okay, so I have two different trim types. I'm going to have a linear trim type, and then also an equal percentage trim type. And I'm just going to create a new function. Flin is a function of x, and that's just going to be equal to x. Okay, so that's going to be my lift, and it's just a linear valve. And then I have another one which is equal percentage, and that's going to also be a function of x. And I'm just going to use an r value of 20 here, and put that to the x minus 1, to the exponent of x minus 1. Okay, so if I just go back here, I didn't really talk about what f of L was, but here I have my lift function, and that's going to be equal to L if it's a linear valve. Okay, and f of L is going to equal to r to the L minus 1 if it's an equal percentage valve. Okay, and the value of R typically ranges between it's about less than 50 and greater than or equal to 20. These are just different trim types here for the if you have a different R value. Okay, so you have different types of valves, and what we want to see is which valve is going to create the most linear installed characteristic. So if I just go back up here, if you remember, the thing that I wanted was lift and flow. I want something that's going to be the most linear. Okay, so I want to evaluate that for my installed valve. Okay, and let me go back to Matlab now. Okay, so we have these two different trim types that we're going to evaluate. And so if I, for example, evaluate F of EP at a lift of 0.5, okay, and I'm going to display that and run it, I get that function is equal to 0.2236, okay, at a value of 0.05 or 0.5, and if I did the same for linear, then it's going to be 0.5. Okay, so let me make that a little bit bigger. So I had 0.5 for the linear and 0.2236 for the equal percentage. Okay, so what I want to do is also just create a couple different values of lift. Okay, so I'm just going to create linearly spaced values between 0 and 1. Now if I do that for 10 values, that's a third optional argument. Then if I just print out lift, then I'm going to see that lift is going to be between 0 and 1, and there are 10 values that are between 0 and 1. Okay, I'm just going to create, let's see, let's put in lift here for my equal percentage, and then also my linear valve as well. And when I run that, it gives me an error. And it says inputs must be scalar and a square matrix. So it says use the dot power instead. So what this dot power does is it essentially just makes it so it operates on these element-wise. So as you call that function with a vector, it's going to take each element of that vector and then return that in F sub E sub P. Okay, so I have my lift values, and then for the linear valve, and then for the equal percentage valve, I have those values. So let's just go ahead and create a plot with these values, just to be able to look at them. And I want to go ahead and get rid of these. If you leave off this third argument, then it's going to do 100 values between 0 and 1. So I'll just do 100 values for the lift. And let's go ahead and create a new figure just to see the lift versus F of L functions for both of these. So I'm going to create a new figure, and I'll just make a title, and we'll just call this valve performance not installed. Okay, so the valve is not installed. We just want to see the lift versus F of L correlations. And I'm going to create actually two subplots here. So I make a 2x1 window, so 2 rows, 1 column subplot, and let's visit the first window, and I'll plot lift and F linear, okay, of lift. And let me just make that a blue line. Okay, and then I'm going to hold on to that result and then plot something else on this same plot. Okay, so if you don't put the hold on there, then it's going to just replace it with this other plot, but we want both of them to show up onto the same plot. Okay, so let me do a dashed line, and let me also do a Y label, and that is going to be F of L. Okay, and then I'll also do a legend, okay, just to be able to show the value, which ones are which. Okay, so that's a linear valve, and I'll also have an equal percentage. Okay, so let's go ahead and run this now. Oh, I had an error here. Let's see, it needs, let's see, undefined function FEQ. of lift. Oh, I had equal EP. Okay. Equal percentage. Okay, so let's just go ahead and do that, and I see a linear valve and equal percentage. And let's just keep, let's add our next subplot as well. Okay, so we're going to have, we want to also see the flow rate through the valves, not just the F of L. Okay, so I'm going to define a specific gravity of 1.1. Okay, now for water it would be close to 1. This is just a different substance, and I'm going to create a new function, which is my characteristic equation for my valve. And I'm going to create this as a function of the following variables. So I have X, I'm going to call that lift. F is going to be my F of L, CV for my valve, and then the delta PV, the pressure drop across the valve. So I have CV times F of X, okay, or lift, and times the square root of dPV divided by the specific gravity. Okay, so there's my flow through a valve equation. And let's go ahead and just define a couple other parameters as well. I'm just going to call the total pressure drop is going to be equal to 200 bar, and that's just going to remain constant. I'll say that the CV of my valve is 2. I'm just arbitrarily defining these at this point. And then let's go ahead and define the flow of our linear valve, and that's going to be Q. And I'll put my lift values in there, and I'll have my linear F of L and a CV value, and then also the total pressure drop across that valve, which is the pressure generated by the pump. Okay, and then I also want the flow for my equal percentage valve, and that's going to be very similar to this last one, but I just replace it with my equal percentage function, and the total pressure and the CV is going to be the same. Okay, and then let's generate the second subplot now. We want to go into the second window. We saw that that wasn't yet populated, and then let's go ahead and just plot lift. We'll do flow linear, and I'll do blue line for the linear valve, and I'll hold on, and I'll do a red dashed line for the equal percentage. Okay, and let me just go ahead and add a Y label. That's going to be flow, and legend. I think I can just copy it from above for the linear and equal percentage valves. Okay, so I have my legend, and I'm also going to put an X label here as well, and that's going to be my lift. Okay, so let's just run this, and we see that we have linear valve versus equal percentages is just the lift L versus F of L, and then here's the flow rate through the valve. So if I have it 100% opened, then that's going to be 25 flow rate. Okay, so now what we want to do is add the equipment as well. So this is our valve without any equipment. So if we just hooked it up to this pump and just had a flow loop going with our pump, this is the performance. Okay, so you can see that the linear valve is going to be have a lift to flow that's going to be very linear, but the equal percentage is going to be not linear. Okay, so we want to compare this to what happens when we install the equipment. Okay, so the total flow is going to drop because there's going to be some additional pressure drop across the equipment. Okay, but let's just see what happens to the shape of these two, and which one's going to be desirable. Okay, so I'm going to go back to my script now, and let's just go ahead and define my C1 value. Let's just say that's going to be equal to 2. That was, if I go back here, that was just, okay, so C1, that was just the pressure. It was a correlation that goes into the pressure drop across the equipment. Okay, it's just empirically determined. And then I'm also going to get dp of across my equipment. I'm going to just create a new function as a function of q. I'm going to call that the expression is c1 times q, and I want to be able to pass in vectors, and so I do the dot power. And so there's my function for my equipment. And then let's go ahead and do the combined valve and process equipment. So I'm just going to implement this equation up here, just simplified and slightly rearranged. Okay, so if I do that, then let me come back here, and I'm going to say qi equals, and that's going to be a function of x, which is my lift, the f of l that I have, and also cv. Okay, so I'm going to do cv times f of, this is my f of l function, and then I'm going to have to square it, and then this is just a rearranged version of that other one that you just saw. Okay, and see. Okay, f of x. Okay, I think that's the function there. And then let's go ahead and just calculate the flow for the linear. And that's just going to be q installed. And then I have my lift. I'm going to use my f of l function for my linear valve, and then my CV value for that one. And then equal percentage is going to be very similar, except for the f of l value. Okay. And so I have my linear flow and my equal percentage flow. And let me just create a second figure now. Okay, and I'll give this one a title. This is my valve performance, and this one's going to be installed. And I'm going to create a couple subplots now. Let's make 3 plots, subplots in this. The first one is just going to be my lift versus my flow for both my linear and my my equal percentage valve. And I'll do the same red dashed and blue solid line for those. Let's just go ahead and take a look at these. Okay, so I have my equal percentage and my, make this just a little bit bigger, and then also my linear valve. Okay, so this one looks just a little bit more linear, but let's put another line on there just to see how linear it is. Okay, and we could always do an r squared to a linear function, and just compare that quantitatively versus qualitatively. But let's just start with the qualitative. I'm going to do a plot from 0 to 1 for my x, and then 0 to, it looked like it ended about 9.4 there. So that was, I'm just going to do a black line. I'm going to make that line width just a little bit more. So we'll set that to 2. It's by default 1. And then let me add a legend. Okay, so this one's going to be linear valve versus equal percentage valve. And let me add a y label as well. And that's going to be flow. Okay, so when I run it, let's go ahead and make this just a little bit bigger. I'll move the legend out of the way. So you can see that the equal percentage valve now has a lift versus flow that's much more linear than the linear valve. Okay, let's just add a couple additional plots just to try to understand why that is. Okay, so I'm going to add a couple more subplots here. I'll go into my second window now in this 3 rows and 1 column subplot. And so let's add lift versus, and then I want to plot the pressure drop across the valve. Okay, so I have my total pressure drop, and then I have my pressure drop across the equipment. So this quantity is going to be the pressure drop across the valve. Okay, so this is the amount that's generated, and this is the amount that's dissipated across the equipment, and so the difference between those two has to be what's across the valve. And I'm just going to do a black dashed line. Okay, and then I'll hold on to that, and let me just do the equipment as well. Okay, so I want to look at the pressure drop across the equipment and across the valve, and I'll just change that to a green. I'll just change that to a green line. Okay, and so I run that. Okay, so here's for the linear valve. You can see as the lift starts increasing, the pressure drop across the valve when it's closed is all 200 bar. Okay, and then as it starts opening, you can see that the pressure drop is going to decrease, but then the pressure drop across the equipment is going to increase. Okay, so that's for this linear valve here. This is going to be the valve and the equipment. And let's do that for the equal percentage valve as well. Okay, so I'm going to come in here and do another subplot, and let me just go ahead and copy these couple lines here, and after I add a legend, okay, so that's going to be valve, that's linear, valve, and process equipment, and then I'm going to do a Y label, and I'll do delta P V. Okay, that's going to be my Y label. And if I go ahead and just copy this and then just replace this with my equal percentage, and I'll just put equal percentage valve. Okay, and then I'll put an X label down on the very bottom one, and that is going to be lift. Okay, so let's go ahead and run this now. Okay, so you can see the installed characteristic of the valve. With the equal percentage, we get a much more linear correlation. So lift versus flow is more linear, and it's going to be easier to tune a flow control loop with that more linear profile. And then you can see the pressure drop, the delta PV, for both the process equipment and the linear valve or equal percentage valve. Okay, so the reason why the equal percentage valve works better in this case is that it starts to have, it opens just a little bit slower than the linear valve, so it compensates for that Q squared value for the pressure drop of the process equipment. So as the flow rate increases, you get this Q squared effect. It's proportional to Q squared for a lot of process equipment. So as you double the flow rate, you might quadruple the pressure drop across the equipment, and so the valve is going to open slowly at first and then very fast in the later lift ranges. Okay, and what that does is it makes a more linear profile overall for the valve. Okay, so that concludes this this demonstration within Matlab. If you want to download this script, the material is here at the APMonitor.com website under the process control course, and if you go down to class 9, I'll post the Matlab files for this tutorial here.